Okay, so today's topic is not about the mechanical properties, but I'm going to explain to you mechanical properties of materials, just to know what those properties are. And I've given a homework for you to answer the questions. Okay, through those questions, you have to read chapter 3 in the textbook, chapter 3. Okay, to be familiar with things that I have highlighted in the homework. Uh, okay, I've highlighted in the homework in a form of questions. In a form of questions. So you have to answer those questions. Okay. So once you read the question, you have to find the relative topic to that question so that you could understand the topic and then reply the question or answer the question in the homework. Okay. Given in the homework. So the first thing is about, as I mentioned to you, mechanical properties of materials. Oh, sorry. What's going on? Mechanical properties of the material. So what we need to know about is the forward scrolling. Okay, the tension and compression test, the first thing that we need to know about. So we always test a sample, an element made of any material that we would like to test. It could be steel, it could be aluminum, it could be anything. And then we have to know the testing machine. It looks like this as an example. We place the sample somewhere within the testing machine, and the testing machine is capable of applying for a force, okay, incrementally. Okay, you have to read and understand how the machine works, how they take the measurement of strain, and how they take the measurement of stress. And then you, at the end, you come up with stress-strain relationship. You have a set of like stresses, and you have a set of strains, data, okay, and then how you relate them, you use a diagram. Okay, you use a diagram. Usually convert the data that you have got from the reading, okay, from the readings that you've got out of the test, and you convert it into a diagram. Okay, you convert all those readings into a diagram like this. To magnify the diagram, you could look at this. Okay, I over magnified for you to see. So in the homework, I've given questions like, what is elastic region? What is yielding stress? What is strain hardening? What is necking? What is proportional limit, for example? So you have to, the question is like this: explain all of the indicated stuff, whatever is indicated to in within this figure, and explain it to me briefly, not in fine details, just briefly. What stress? What is the proportional limit of this stress? What is meant by yielding stress? What is meant by fracture stress? What is meant by ultimate stress? Okay, so you go to the text, the content within which you could find those information, and you simplify, oversimplify with your own language. You answer the questions with your own language. Okay, so that is just for you to understand what is this stress strain, why we need to have this stress strain. Of course, we will not make use of it in our following chapter, but we need to have an understanding of this stress strain relationship, what elasticity is, this capital E, modulus of elasticity. Okay, so that's basically what I want you to do in the homework, nothing else. Okay, that's all what I want you to do. It's just for your knowledge, your background, because most of the time we deal with the mathematical problems, but we sometimes need to have some background about what is stress, what is strain, not mathematically, but as an engineer, we have to understand why do we need this relationship between stress and strain, why we conduct tests, why we conduct compression and tensile tests as an example, and so forth. And also I've given like what is the difference between like this kind of failure, it happens to ductile material, and what is the difference between the material that is not ductile, which means the material that is brittle. Okay, and this is the tension failure of a brittle material. This is how a brittle material would fail unlike the ductile one. Okay, so you have to explain why, what is brittle, what is ductile, not mathematically, but as an engineer, how can you explain it? Of course, in a very professional way, you have to explain it. Okay, so that's what I want you to understand. What else? What is stiffness? What is strain hardening? I have given this figure as an example. Why do we have this? Explain to me this figure. What is meant by it? So you have to read the content that is relevant to this figure, which is strain hardening. So you go through the content and see what is talking about the content, what we have in the content, and then you explain to me this graph based on your understanding with your own language in a simplified way, very simple explanation as an engineer. Okay, as an engineer, okay, I want to have a professional way of explanation. Okay, not mathematicals. There would be no mathematicals. If there's any mathematical, you could also include if there's any formula. Okay, that's all. Okay, that's all. So this is what I wanted to let you know. Nothing more than this. Okay, this is like you have to have this background. It's not it's not just about solving problems. You have to do some readings. So it's a self study. The thing is, this chapter is a self study. Okay, this mechanical properties of materials. Anything that you can get, I can explain it to you later on. Okay. Anything that you find it difficult to comprehend or understand, I could explain it to you later on, because this kind of mechanical properties of materials, you will all the time need it even when you go to when you study reinforced concrete design, you have to understand the graph I've shown to you just now, which is this one, this graph, the magnified one is this one. Okay, this graph, you all the time, you need to understand how steel behaves. Okay, this is almost, you could say, how steel behaves in terms of stress and strain, and also you need to understand how concrete behave if you are studying reinforced concrete design, how concrete behaves when it comes to compression and tension. This is concrete and compression, how it behaves. So stress versus strain, and this is the graph for concrete and tension, stress versus strain. Okay, so that's all. Okay, we move to the next chapter, which is so this is chapter 3. We move to chapter 4. Okay, axial load. I will use the textbook to explain to you this chapter, which is almost has the same content with the PPT uh, PPT with the PPT slides. Okay, the PowerPoint slides, the same content, so it's more convenient for me to make use of the textbooks. That's why I'm using the textbook. So today's topic is axial load, axial load, axial load. ديدار لقال يحيى دائم تأخيريا يعني all the time behind the students 20 minutes يعني أولي يبلي 9 minutes 5 minutes 6 minutes ديدار يحيى all the time late. This is a negative point. Okay. Okay, so now we talk. Today's lecture is about axial load. So that means you studied the elements, the members that are axially loaded. Okay, and the relevant deformation. Relevant deformation. So now we need to understand, if you have axially loaded member, we know what axially loaded member is, right? Is there anyone who doesn't understand what is meant by an axially loaded member? Axially loaded is like we have this element, okay? It's not transversely loaded. It's not loaded this way. It's axially loaded along the longest axis. Which one is the longest axis? If I take a cross section and assume it to be a rectangle or a square, okay? Assume it to be a rectangle or a square. if the cross section is rectangular, has a rectangular shape or square shape. So the longest axis would be the length, right? So any load that is along the length of the element, that load is considered to be an axial load for that element is an axial. So P1 and P2, they are axial loads, okay? So this member is axially loaded. That is what is meant by axially loaded members, okay? Anyone who doesn't understand axially loaded, let me know. Okay, if you understand what axial loaded, that is fine. So that is our topic for today. Okay, that is our topic for today. So if you have a member like this, okay, it's for example is fixed at the end, and you have an applied load, axially loaded. This member is axially loaded, so this is an axial load, and it's a tensile force. It's pulling the member upward, and the base is fixed. Assume it to be fixed. Okay. So if you look at the stress distribution, stress, we know stress, normal stress is equal to force over area, right? Force over area. So that's what stress is about. We know it. So if we look at this principle, the so-called Saint-Venant's principle, what Saint-Venant's principle says, it says that we assume that the stress is uniformly distributed along the cross section, is uniformly distributed. If you look at no, clear all, okay. What is meant by uniformly distributed? How can we, if you look at, this is where the element, the section is taken close to the load application, where the load is applied, okay. If you look at this section a bit farther from the point the load is applied, it's a bit farther from the point, and then this one is farther from the load application or the location of the load application. You see the section that is close to the load application in terms of location, it's close to it. You see the stress distribution is not uniform, right? The stress distribution is not uniform. You see that the stress is low at the edge and it increases up to the maximum at the middle, then goes down, or I mean goes up, the stresses goes up, or in terms of value, it goes down to the minimum again. So you have minimum at the edge and maximum at the mid-span or the mid of the section, okay? At the midsection, you have the maximum stress and you have the lowest at the edge. Okay, if we look at the shape just now, you said that this is the member, okay? This is the load applied. So if you look at those grids, these lines, vertical, horizontal lines, okay, these are the grids. If you look at the grid, you see, you could imagine that the stress at the edges are the lowest, but the stress in the mid is the highest. And could you explain to me why would it be that way? Why would the stress at the edges be at its highest while the stress in the midspan or the mid cross section is at it's highest at midspan and lowest at the edge? Could you tell me why would it be like that? Zam, come on here. Who is willing to answer this question? Huh? Sina? Why the stress distribution is not uniform close to the load application? When the location is close, is nearby the load application, why the stress distribution is not uniform? As you understand what is meant by not uniform. That means the stress is at its lowest at the edge, these two edge, here and there, and then it increases up to the maximum, then back in terms of values goes down, and in terms of shape goes up. Why would we have the maximum at the midst and we have the least at the edges?
Teacher, والله يعني I don't know.
You don't know. Okay, who else could explain it? Very simple. You could visually visually explain it to me. You don't need to have any engineering background to explain it. I mean, it makes a bit. You could say there's some common sense.
أستاذ
Make you Reba.
والله أستاذ لبر أوي هيزكا لنا عراس تبعه زيادة الرزق لنا عراس زكاة
Yeah,
هو
exactly.
هيزا
Exactly. I got you. Because the force is acting at mid, so the closest the location is from the force application, the higher the stress is. Okay, simply because of the location of the force. And then why would it get uniform? The when the how to say when the section is far away from the load application, why would it get more uniform? It's not yet completely uniform, but it is more uniform. You can see it's getting a little bit more uniform because the least at the edge is getting larger and the highest at the mid is getting, like, not to say smaller, but it's getting equal to the edge stress. And then the farther we get, the far away, the more far away we get from the load application, the more uniform it gets, the more uniform it gets, and stress distribution becomes more uniform. Any explanation for that? I mean, this is based on your common sense. I mean, visually, if you look at it, you can feel it, you can detect it easily. You don't need to have a mathematical formula to explain it to you. Just easily, you could say, as just now Reba said, because of the load is at the mid section is applied. So that's why most of the stresses are concentrated in the mid, right? While the stresses at the edge, they are far away from the load, so they are getting less, less influence from the load. That is why you have non-uniform distribution for the stress, non-uniform. But when the section is getting far, I mean, if you look at the element, you will feel it. The closer you get to the load, the more distorted the grid is. This line is the grid line, this horizontal line, and you have these vertical lines, okay? They are making grid, okay? We have a grid because of these vertical and horizontal lines. So if you look at the grid, the first line of the grid is close to the load application. It's the most distorted one. The second line is less distorted. It's still distorted, but less. And the third, you see, is getting less distorted. And the fourth, almost you could see minimal amount of distortion. And the fifth, no distortion. You can't feel. Why? Because we are getting far away from the application, from the load application. That's why. And then when we reach section C, the force distribution or the stress distribution would be uniform. So that means the whole cross section will receive the same amount of influence from this force. The whole section would receive the same influence, the same amount of influence. Okay? That is the point. So now we can understand that the farther we get, the more influence, the influence will be distributed across the section. Okay? The closer we get to the load application, the more influence part would be the one which is the closest one to the load application. Okay, so the principle of Saint-Venant's principle, he said that, well, since that the load application location at the edge that is close to the load application is influenced by the load location, that the stress distribution is influenced, we consider that the stress distribution along the cross section is uniformly distributed right from the beginning till the end. So he ignores this influence. That's the principle of Saint Venant. This is Saint Venant's principle, that we ignore this minimal amount of distortion that you can see over here is ignored when you get far. I mean, is ignored right from the beginning. Is ignored right from the beginning. Right from here, he ignores this. He ignores this. He doesn't take this. Because if you take this, you need to calculate use some mathematical formula, or there must be a way out to determine how much of the force is going to the mid span and how much of this is going to these two sides, right? Using your your engineering mechanics background, you could calculate maybe based on the reaction, you get like P over 2 over here and there, while over here you'll get like equivalent amount of stress, but in the opposite direction and so forth. That could be one of the way that we could use to know how the stress is distributed. But based on the Saint Venant's principle, we don't need to think of this distorted line or this non-uniform distribution. You just think of it as if wherever the section is taken, we consider that the stress is uniformly distributed. Okay? Is it okay up to now? That's the whole thing. We consider that wherever the section is taken, close to the load application or far from the load application. Okay, we will get this stress is equal P over A. It's not like we don't have such a distribution. Okay, based on Saint Venant's, this is negligible. We ignore it. Okay, it is taking place in reality, but it has a minimal effect because it's only when it gets close to the load application. Only when it gets close to the load application. The farther you get, or the far away you get, the less effect it would have. The force location would have less effect, and that's why you see that he has considered this stress distribution, which is uniform. Uniform. Okay, that's all. Even if you look at these two forces, okay, you have P over 2, P over 2. So he says, Saint Venant says, okay, hence we have P over 2 added to P over 2, so it's the same like P. So it'll get the same amount of stress. Okay. Because if you look at this, if you get close to this point, the stress distribution might be like this. If this is our bench line or benchmark, okay, a stress distribution could be like this. From least, this is max, and this is probably getting down a bit. It could be this, sorry, could be this way. Okay, this is wrong. So the stress distribution is like this. But we still consider the stress distribution to be uniform, based on Saint Venant's principle. Okay, could be less of uniformity. Okay, so this is not a uniform, but based on Saint Venant's, we consider that the stress distribution is uniform. We don't consider this kind of distribution. Okay, we don't consider this kind of. We just consider the uniform distribution of the stress along the cross section. Okay. Okay, so now we understood. Now we move to the real subject, which is elastic deformation of an axially loaded member. Okay, we have an axial load applied to a member, so definitely if you apply an axial load and the load is tensile, for example, is pulling apart the member, so there would be some change in length, right? There would be some change in length, and that would be elongation. The change in length would be elongation, right? If the force is tensile, is pulling apart, right? Is a tensile force and pulling apart. If the force is compressive, if there's no compressive, okay, if the force is compressive, instead of having elongation, we will have contraction. Instead of having elongation, if the force wasn't a tensile force, it was a compressive force. So it's like pushing the element, okay, close to each other, to this end to this end, right? So instead of having the elongation, we will have contraction. Instead of change in length, same thing, same concept. Change in length, instead of elongation or expansion, we will have contraction, decrease in length. Contraction, okay? Contraction is decrease in length. So it depends on the force. But in general, be it tensile, be it compression, be it tensile or compressive, you will have change in length, okay? If tensile expansion, if the force is compressive, then contraction, okay? That's the principle of an axially loaded member. That's what kind of deformation. And then we end up with a formula. We can calculate this formula based on, we can calculate the deformation based on this formula, which is NL or PL, okay, the force times the length of the element over the cross-sectional area times the modulus of elasticity. Okay, so the only thing that we are not familiar with is the modulus of elasticity, E. Okay, E is modulus of elasticity. E is equal to stress over strain. Okay, stress over strain, right? So this is modulus of elasticity. So that means stress is equal to what? Modulus of elasticity, E times strain, right? And if we apply this stress is equal to normal